What's up, gentlemen? We're here to make the chapter 2 homework key. This is the first chapter 2 homework, but let me just go ahead and say up here at the top. This is chapter 2, homework number 1. Let's check her out. First one, we want to know what has more angle strain. Cyclopropane or cyclopropene? Which one of these has more angle strain? Well, in this one, so let me call these A and B. In this one, all the carbons are sp3, right? In this one, we have an sp3 carbon and 2 sp2 carbons. So what we need to think about is, first of all, what is our forced bond angle here? This is the bond angle that it has to adopt to make this triangle. So this is a forced bond angle of 60 degrees. And then what are the ideal bond angles for each of these structures? So ideal bond angle for A, if it's sp3, should be 109.5 degrees. For B, our ideal bond angle should be, for sp2, it's what? 120 degrees. Okay, so B, this one is farther, well, let me say this way. 60 degrees is our forced bond angle. Okay, it's farther from 120 degrees than it is from 109.5 degrees. So structure B, this is forced into bond angles significantly smaller than what it would like to have by Vespers by maximum repulsion. So B is our more strained structure. Okay, that was pretty easy, wasn't it? 36. What does number 36 ask me? 36. Add dash wedge notation to each line structure to provide directly to predict small sigma appearing above it. Okay. So the first structure that we're given is this guy. Okay. So then there's like a carbon in the middle, and then it's double bonded over here to these two Fs. So I put that dot in the middle. That's not really a normal notation thing. I put that there to denote that that is a unique carbon. If you wanted, you could just draw a carbon there. That would be fine too. Okay, so there is a carbon in the middle. For line wedge dash notation, this one's a little bit weird. So there's like a twist at this center carbon. Okay, because the central carbon, if you think about it, the central carbon has to make a pi bond in this direction and has to make a pi bond in this direction. So if we bring in a little bit of the chapter 3 stuff that we know not now, we have to make a pi bond in this direction. So that could use the let's say one of the pi bonds, let's say the one to the left, uses the p orbitals that are in the plane of the paper. Okay, so if we're using the p orbitals in the plane of the paper to make the pi bond going this way, then what p orbitals are left behind to make my sigma bonds when they hybridize with the s orbital? Well, then I have my perpendicular one, right, that's going straight into the paper, that's sort of left behind to make the rest of the bonds, the sigma bonds to the fluorines. Okay, so that's going to give those hybrid orbitals, then they're going to have some dimension that's sort of going in and out of the page instead of being flat on the page. So one side of this needs to have its fluorine sort of coming in and out of the page. Okay, there's sort of, like I said, a twist in this molecule in the middle because of the fact that it's making a pi bond with two separate carbons. Okay, then this carbon on this side, it would have to use its perpendicular pi orbital to make the pi, or p orbital, I should say, to make the pi bond, and that leaves then this in-plane p orbital to hybridize to make in-plane bonds with the Fs. Okay, so that one's a little bit unusual that it has this sort of twist, but that's what we're looking at. Okay, next one for B. Okay, I'll just draw what we start with here. Okay, this is my starting structure. If I want to write this in line wedge dash notation, then I'm going to keep my longest chain in the plane of the paper, okay, which is 6. Then looking at this ball and stick model in the textbook, it looks like this carbon is coming towards me. So that guy would get a wedge. And since it's a methyl group, I can just leave it like this. This wedge is implying there's a CH3 at the end. And then this carbon, it draws that one as kind of going into the page. Okay, so it would look like that. Okay, number C. Let's go on to number C. So on number C, we have this little guy, this little epoxide. We'll get to know epoxides next semester. Well, you guys will. I don't know what my role will be in this class at that point. But you guys will learn about epoxides. What does this guy look like on the textbook? The textbook kind of shows these methyl groups are coming towards me, and these are not meant to be wedges right here. This is just where I try to make my line look a little bit straighter. Okay, the textbook has the ring with the oxygen in the plane of the page. That's what their ball and stick model looks like to me anyway. And it has this coming out at me. It's coming out of the page. And it has this coming out of the page. Okay, so those are coming towards us. I think that's what it's trying to represent. That's what it looks like it's trying to represent. And then it has these H's kind of going into the back. Now, remember, we don't have to show that explicitly because that's where we would assume they are, because the other 3 bonds on this carbon are already explicitly shown. These 2 are in the plane. This one's coming out of the page, so the H's have to be going into the page. So we don't really have to draw those H's. Again, I just drew that to kind of illustrate, hopefully, a little more clearly what the book has. Okay, last one. This cyclopentane with an amine on it and a 3-carbon chain coming off of it. The only thing I can see here, it looks like this ring is in the plane, this chain is in the plane, and then the nitrogen is going back into the page. So it looks like that. That's what I'm seeing here. That's what this drawing means to me, or a ball and stick model means to me. Okay, let's move on. So that's 36. 37. My old rickety dot cam hopefully doesn't fall over on me. 37, we are rotating. I mean 37A. 37A, we are rotating something. So, and we got an OH, we got double bond O. We got a bunch of dashed OHs, so dash, 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 wedge. And the book wants me to take this guy and rotate it like this. Did I draw that right? No. Wants me to take this guy and rotate it like this, 180 degrees. So it wants me to take this and kind of flip it this way. Okay, flip it like hamburger way on the paper, not hot. Is that even hot? Yeah, hamburger way, not hot dog way. So we want to flip this molecule like this. We're just going to take this and kind of twist it around. So all these OHs that are pointing into the page, okay, if I take this and flip it, they're all going to be pointing out of the page. Same deal, this guy that's pointing out of the page at me is going to then be sticking into the page. And then the entire molecule is also going to be like mirrored 180 degrees. So now this H is going to be down instead of up. This O is going to be pointing up instead of down. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 to the OH. And then this OH, like I said, this is now pointing towards out of the paper into my face, out of the paper into my face, face, and then this one's going to be pointing into the paper through the desk into the floor. Okay, that's not so bad. 38, we want to rank. So 38, we're ranking BF3. Hey, remember boron? We talked a lot about boron last year, didn't we? We'll talk more about him later. BF2H and BFH2 by from, excuse me, least polar to most polar. Well, let's draw these. Boron, these types of boron structures, what's the hybridization of this boron? Because remember, this is not like a nitrogen. It's not like a group 5 element. This is a group 3 element. So it doesn't actually make, it doesn't have a lone pair. It just makes 3 bonds, and then it has an empty p orbital. So this is sp2, right? It's using its s and its 2 p orbitals to bond to make these sigma bonds, and then it has a leftover empty p orbital that doesn't do anything. Okay, because remember we talked all about how this is a good Lewis acid. It wants to accept something into its empty p orbital and become a tetrahedral boron. Okay, so these things that I chose to talk about last semester, we talked about them for a reason. But anyway, let's answer this question. Let's stop whatever it is I'm talking about right now. Which one's the most polar? Okay, definitely not this one, right? These are all sp2s, so these are all trigonal planar. Okay, they're all trigonal planar, spaced out 120 degrees from each other. Fluorine is more electronegative than anybody else, so we don't even need to consult our periodic table. And we should see that these all cancel, which means overall this is non-polar. Okay. This one, again, we're going towards the fluorines. Okay, so really like the top side of this boron is going to be really partial negative. Down here it's going to be pretty partial positive. Over here we just have one fluorine pulling in that direction. Okay, so we're going to end up with a partial negative basically on that fluorine. Over here we have this combined force of these two fluorines that are both pulling in the net direction together. Okay, so this is going to be the most polar, and this is going to be in the middle. So we'll say it's still polar, but it's less polar than this guy was. Okay, it's got more fluorines, as pointed out. Okay, number 39. Okay, 39, I could see, if I was you, I could see how 39 is a little confusing after what we just said in 38, because 39 wants us to determine which of these guys is more, I think it just says which is more polar. Yeah. But it says why is one more polar than the other. So it tells us the dipole moment in Debye. Okay, so this one is more polar, which is weird considering what we were just saying up here, right? Because this one has 2Fs and this was the most polar. Down here, this one has 2 oxygens, which are more electronegative than carbon, right? So you might intuitively try to think that this one is more polar. So let's look at the individual bond dipoles and see if this makes any sense. This one's going up towards the oxygens, and beyond that, the carbons are going to be pulling slightly on the hydrogens, but we won't ever really consider that in trying to draw a molecule's polarity or its dipole moment. This one, same idea. It's pulling up towards the oxygen. Okay, then this oxygen is also pulling on the same carbon. Okay, so right now we could think of this as sort of looking similar to this and wondering why that doesn't result in a stronger dipole. Okay, it's because this oxygen is also pulling on this carbon. So we end up with a bunch of sort of conflicting arrows, right? If I try to draw all 3 of these arrows, these vectors out, or if I try to just add these vectors together, they're kind of partially canceling each other to where I just have a slighter dipole going up towards this carbonyl oxygen. Okay, so I'll say the bond dipoles partially cancel. We have a more complicated geometry here than we did in the case of boron. Okay, where we just said our overall they're they're pointing opposite left to right, but they're both pointing in the same vertical direction, which gives us a kind of a strong dipole. Here we have kind of a bunch of different partially canceling dipoles, so it ends up being weaker. Okay, hopefully that makes sense. Okay, last one, 41. Is 41 the last one? 41's the last one. This is just kind of fast for a video key for me, it seems like. 41. Determine whether each of the following molecules is polar, and if polar, say where is it polar. Okay, so our first guy is this trans difluoroethene. So we have, make this a little cleaner looking here. We have polar, right, or very electronegative fluorines, and we see that those vectors are going to perfectly cancel each other out. Okay, so when our vectors cancel each other out, we end up with a non-polar molecule. They're pulling exactly equally in opposite directions. Compare that to the cis difluoro in B, okay, where both the fluorines are pulling down. Then overall, and I'll draw the overall one to the right in each case. Overall, my left to right components cancel, my up and down components add together, so overall I get a dipole pointing down. So this is polar. Okay, so there's a cis difluoro, trans difluoro. Did I call this trans difluoro? I think I might have said the wrong thing earlier. So this is the cis difluoro, this is the trans difluoro. You might be wondering, and we're not going to talk about its dipole, but I just wanted to tell you this because I didn't have time to say it in lecture the other day. What if they're on the same carbon? What do we call that? Okay, this is called a gem difluoroethene. Okay, it's geminal, meaning that they're on the same carbon. Right? It's, you think of, if any of you guys are into horoscopes, I'm certainly not saying that I am. I'm not. Okay, I'm going to actually explicitly say I'm not into horoscopes. But this does remind us of the word Gemini a little bit, right? Meaning twin. They're kind of twins on the same carbon. That's where that name comes from. Do you need to know this? At least not right now. You don't. But in case you were wondering what the other situation is besides just cis and trans, you can also have gem. Okay, that gets its own little special name. Okay, moving along. So this was A. This is B. Next one will be C. This is dichloroethine, or acetylene is our trivial name for this 2-carbon with triple bond. Okay, so remember this is a linear structure. The chlorines are going to be pulling opposite directions, which is going to make this nonpolar. Okay, easy enough. D looks like this. So similar idea, except now, and I'm not going to give the name of this one because now they're starting to get too long if I do this every single time. Well, I mean, really, well, I guess we could. This would be like 1-chloro, 1-propyne, right? Because anyway, 1-chloro, 1-propyne. So the big difference is now we're pulling towards the chlorine. The methyl group's not doing anything. Okay, right? This carbon and carbon. I mean, honestly, really, this is probably pulling a little bit towards this more electronegative, electron deficient sp carbon based on what we've talked about previously. But let's not make the picture more confusing here. Overall, we for sure have a dipole pointing to the left. Okay, so this is going to be polar. E is this. Okay, so chlorine is closer to fluorine than bromine is. So the chlorine vector is going to be bigger, right? It's going to, electrons are pulling more towards chlorine than they are towards bromine, which means that overall, okay, this would be my overall net dipole. It's towards the chlorine. I guess I didn't draw this very well. It should be a little bit smaller than this bond dipole. But overall, again, we're pointing towards the chlorine, so this is going to be polar. It's going to be slightly polar, certainly less polar than D. Okay, that was E. F is nonpolar. I'm not even going to redraw it. It doesn't even have any heteroatoms in it. It's just all carbons and hydrogens. Anytime you have all carbons and hydrogens, you are nonpolar. G. Okay, so again, another super important note while I draw G, because I saw a couple people do this, and I believe I wrote it on your paper to remind you that you have sinned. Okay, if I don't draw my double bonds in here, if I just try to finish my structure like this, that is not the same molecule as what's in the textbook. The textbook has double bonds going across these rings, so it's like I have these two benzenes fused together. Okay, you have to always draw in. You see I'm hitting the desk, the camera's vibrating. Okay, you have to always draw in the double bonds or you will lose points. I promise you Dr. Wysocki and I will both take points off for that. Maybe not both on the same problem, but we agree on this is what I'm trying to say. Make sure you draw in all your double bonds. Okay, chlorine we know is more electronegative, so we're going to be shifting towards the chlorine. Net dipole is going to look like this. So this is for sure also then polar. Hang on, somebody's calling me. Okay, I don't know why I even look at my phone and people call me. It's always just spam calls. You just get spam calls all the time. There was an era when we didn't get spam calls all the time like this, but I guess it's whatever. Okay, H is another one of these fused rings with double bonds. Don't forget the double bonds, please. Except now I have one chlorine up and one chlorine down. Okay, so this one's going to pull this way. This one's going to pull exactly the opposite. So overall, it's going to be non-polar. Right, they cancel. They cancel. Okay, number I, they also cancel. Okay, again, if well, you guys can't even see this. Again, if I stop here, that's not the right molecule. That's cyclohexane. This is benzene. Not the same thing at all. And then I had a bromine here. This is like a 1,3,5 tribromobenzene. Okay, and it's just like we talked about with that BF3 example earlier. They're all pulling in opposite directions, so they cancel. So again, it's nonpolar. Our vectors all cancel when we add them together. Okay, I'm out of room on this paper. Okay, smash cut to me having a new piece of paper. What did we just do? I, so J. This is a cyclobutane. This is a dichlorocyclobutane. And the chlorines are pointing like this. Okay, they're both pointing up towards me out of the paper. So it's kind of hard to picture this, but this one has a dipole pointing to this chlorine up out of the paper. This one's pointing to this other chlorine up out of the paper. So my overall dipole is pointing like right into the camera lens. Okay, so overall, we'll just say arrow coming out of paper. That means it's polar. Okay, its dipole again is kind of like on the same side that these chlorines are pointing would be where the dipole is. J, K is the same idea, except now one of the chlorines is coming out, one of the chlorines is going back into the page. So, okay, now I have one pointing up and one pointing into the page, one pointing down into the page. Okay, so in this case, they cancel because they're pointing opposite directions perpendicular to the paper. So they are perfectly canceling. So this would be nonpolar. L. Now I have one up and one down off my cyclobutane. Right, and they're both kind of pull towards each other. It's just that one is coming slightly up out of the paper, one is going down slightly into the paper. My overall dipole then is just going to be pointing on that same side of the square where the chlorines are, so this is going to be polar as well. M, we have the tetrachloro. Like this. I hope we can see this is nonpolar. They're all going to cancel. Right? It's just like how up here these canceled. Imagine just having another equally canceling pair of chlorines on each carbon. So one coming out of the page here and going into the page here. Then it makes sense that those would cancel. And then N is just like E because we have a bromine side and a chlorine side. Okay. So, you know, it's the same idea. We're pointing kind of in the middle of these two is where our dipole is pointing here. I guess I should have drawn my dipoles over here too and show how they cancel. We're pointing in the middle of these chlorines, so we have a dipole forming over here, or a bond polarity going that way over there. Over here, we have a weaker bond polarity going towards the bromines. I can't speak. Let me take a little drink of water. Okay, we have the bromines are less electronegative than the chlorines, right? They're farther on the periodic table from fluorine, so the net dipole then is just going to be going towards the chlorines, which is just going to be a little bit weak. and this is going to also be polar. Okay, so there's your first homework key. But before I go, okay, I just want to point out when I'm looking at my YouTube analytics, I noticed that only 10% of the people that watch my videos are subscribed. No, I'm just kidding. Don't subscribe, don't like, I don't care. Just watch the video and learn something. And if you have questions, please don't hesitate to ask me. And, thanks for watching, and I'll see you at the next homework key.